Hi there, this is exercise 3A, and we're going to do it in two bashes, hence the point 1 on the screen. But basically we're going to look at transformations, and transformations are something we saw at GCSE, and also then we saw it at when we were using the Year 12 textbook. And now using this Year 13 textbook, this goes a little bit further and expects you to, first of all, it expects you to know more functions and also more transformations and more combinations of transformations. I suppose it's the combinations of transformations we're going to look at in particular. So anyway, let's see what we can do. Just a brief starter on this. These are transformations we've seen in the past already. You might remember them. I'm just looking here, for instance. This would be typically, if I started off with y equals, I don't know, x squared, what would, for instance, it would be if I just times by a number at the front, say 4x squared. And you should know that that is a stretch. This one, by the way, this one might be equivalent of saying y equals, you might put it in a bracket like x plus 2 all squared plus 6. Notice it's very similar, but my function now is very particular. Now, that first one, if I was to do this one, is a translation. It goes left and right because it's in brackets, and it goes up and down because it's got a translation outside the bracket as well. You may recall that the plus 2 makes it go 2 to the left, hence here it says minus a, translation of minus a, but the number outside, plus 6 in my case, means it goes up 6, so it says plus b, so it goes b. This one here is the one I said was a stretch of scale factor k. Mine was a stretch of scale factor 4. Posh way of saying that it's parallel to the y-axis. The third one, well, this is where, what if you have something like y equals, in brackets, 3, and I put, rather than x, I put 3x, and I substitute the x for 3x for it. Now, you could think of that as just simply multiplying it out and say 9x squared, or you could say it's a stretch of scale factor 1 over k, and now in my case 1 over 3. And if you imagine that it's being stretched left and right, would also, by a scale factor of a third, actually you squash it in, and actually it would look similar to stretching it upwards as well. These last two are reflections. You may recall this one is a reflection, like y equals minus x squared. And that's a reflection of the x-axis. And if I substitute the minus x into my expression, and I write y equals minus x all squared, well, again, actual fact, that has to be a reflection in the y-axis. But again, you could multiply it out, and it's a highlight of the fact that x squared graph would look like this. And if I was to reflect it in the y-axis, it would still look the same, and that's because the equation's the same. So that's what we've seen in the past, and hopefully most of that makes sense for you. Single transformations then, so here's an example of one from what we've seen in the past. I've got the transformation y equals, the graph rather, of y equals 1 over x, and I want to know what I would do to it to get 3 over x, and you should spot that really all I've done to go from there to there is I've kind of done a 3 times by 1 over x. And once you spot that's been multiplied by 3, you go, oh right, when you multiply by 3, it's a stretch. And it's a stretch scale factor of 3, and basically it's going to go up 3 or down 3. When I say that, it's a stretch, it's a multiplication. So here's the posh graph. And if you take any point on this, so for instance, I've taken the point 1 and it's gone to 3, it's become 3. And if I took this point here looks like it's half up. I don't think it quite is actually. It's presumably, no it is, it's normally on the y equals x graph, it'd be 1 over 2, yeah, so that'd normally be a half. And you'll notice now it's 3 times higher, it's 3 halves. And so in all of these cases, and it works over here as well, so if I took this minus 1 point, it goes to minus 3. So just any y number will go 3 times bigger, or 3 times smaller, I suppose, technically that way. So this is like one of the ones I just showed you, because this says describe the transformation to go from y equals x cubed to this point. I suppose the very first thing we need to know is, what does x cubed look like? It goes, oops, that wasn't very good. So it's like that, and then it's like that, and you get this stationary point here. sometimes called a point of inflection, and that's my y equals x cubed graph. And I need to know what happens if I do x minus 2 all cubed plus 1. And again, you notice I've replaced the x with an x minus 2. I put a minus 2 in the bracket. So that will move it right 2. And then, of course, I'll move it up 1 because of the plus 1. So that's my graph, actually. There's my x cubed graph. It's moved over 2 to the right, 1 up. And there's my stationary point. So it is a translation. This is the partial way of describing it by the vector 2, 1. And the stationary point is at 2, 1. So far, not much different from what we've seen before. Let's have a go at this. So this is a bit harder, I suppose, maybe. The graph of y equals x squared minus 6 plus 3 is a translation of that. Right, I suppose we need, if we're going to do... So we start with y equals x squared, and it says, what happens if I write this? And of course, this is not written. Just now we wrote it like this in brackety form and number at the end. And of course, this isn't written like that. So therefore, it's very hard to see what's happened to the x squared. And the way we make it easier is we start with x squared minus 6x plus 3. And I'm just thinking to myself, I'm going to complete the square because it's quadratic. So I'm going to go x minus 3 all squared. Oh, don't forget to take away the 9, the square of the 3. And it says plus 3 already. So that gets me x minus 3 all squared minus 6. Okay then. So that tells me my original graph, which was an x squared graph, is going to go 3 to the right and 6 down. And so it's going to look something like this. And its stationary point will be at, well, 3 comma minus 6. And of course what they want is describe its translation. And I think it's gone 3 to the right and 6. And I think it's C. The next one says, if f of x is a single vertex at 2, 3. So this is one of those ones where they don't even tell you what it looks like. It just says, we've got some, I don't know, it says it's got, anyway, we've got some graph. I don't know what it looks like, but at 2, 3, there, we've got a vertex, a turning point, a stationary point. And it says, what will this be like? Where will it be then? And you've got to say to yourself, well, hang on a bit, I've got two things going on. This, the f of 2x, what will that do? Well, that will squash it in. It will be a scale factor by a scale factor of a half, if you remember, because it's in the brackets. You do the opposite of what you would expect. And that will be in the x direction. So basically the x number, which is presently a 2, will be half as big. So I'm thinking 1 comma something, half of 2. Now it says then f of 2x minus 1. Well, what will that do? Well, that will just move it down 1. It's a translation. So one's a stretch, one's a translation. So it presently is at 2, 3. I reckon it's 1, 2. I reckon it's D. Let's see what the answers say. C and D. Good. So we got them right. More transformations. So this time the graph of f of x is known. Explain in words how the graph of these functions may be obtained from the known graph. So I suppose we need to describe it properly. So the transformations, I think this is just wordy stuff. Those ones describe the transformations. And here it says f of x plus 2. So I'm thinking to myself, that's a translation, 2 to the left. Okay, so I'm going to go 2 to the left. Oh, and it's got a minus 3 outside, and I know it's going to go down by 3. So I'm thinking this is a translation by the vector. You don't need to write by the vector, but you can just say minus 2 and minus 3. So I think that first one's done. That's A, isn't it? What's B going to be? So B, it says, oh right, so this one, again, the nice thing about, I suspect all of these, is you've got two things happening, one left and right, one up and down. The problem comes when you get two in the same direction, and we'll come to that in a bit. But when you've got them both doing it in opposite directions, you don't really mind which order you describe them in. So here I've got 3 times the function. So I'm thinking to myself, okay, that's a stretch. That's a stretch. Now I need to say it's parallel. Now it's outside the bracket, so that's to the y-axis. by a scale factor of 3. Followed by, or before, it doesn't matter which order these are in. And the next one I'm going to say that's, it says -1. That's in the bracket, so it's a translation. And it's 1 down, so 0 across, 1 down. And that's B done. C. Y equals a half, so again it's a stretch by a scale factor of half, up and down. And x over 3, oh right, it's another stretch. But again, it's in different directions. So as soon as it's in different directions, it doesn't matter which order you do it in. So it's a stretch parallel to the y-axis again. Scale factor of, what is it? It's a half. And I also want then a stretch parallel to the x-axis. Now you always do the opposite thing for the x-axis one. So it says we are going to divide by 3 here. So I reckon that means it's a stretch parallel to the x-axis, scale factor of 3. And it does the opposite. It's not a divide, not a third, it's times by 3. And D, now what's this one say? It says y equals 1 minus f of 2x. Now actually, the 1, there's actually 3 things going on here, I think. First of all, I've got this one here. This is a minus. I'm making it a minus. So whatever graph it was, so if it was like that, it's now going to be the opposite. It's going to reflect it. So I'm going to say that first. I'm going to reflect it. I should say for reflection in the x-axis. That's my number 1. Then I'm going to move it up. This is what this is doing. That's translation 1 up. And I'm just following the rules of Bodmas on that, because there's 2 things in the up and y direction. The x-axis thing makes it move up and down. This then it's a translation, and it's 1 0 1 up. And finally, the last one can actually be done at any time. This is a stretch, and that can be done at any time because this one's going left and right in a different direction, so you can do it whatever you like. Parallel to the x-axis. Scale factor. Now it says 2. We do always do the opposite. Scale factor of half. I think that's going to overlap all my answers. All right, you might be just be able to see it. So that one's right. Translation 1 0. It says or vice versa here. So it's translation. I'm looking at B now, thinking I might have got it right. Wrong, sorry. That's x minus 1. I said 0 minus 1. It's actually in the bracket. That was me being stupid. So that means it goes 1 0. That was bad mistake. But that's because it's in the bracket. Therefore, it's left and right. And it's minus 1, so it goes 1 to the right. So stupid mistake by me. And therefore, yes, that's a bad mistake. But other than that, it's right now. Scale factor 3 followed by a yep. And that's right as well. Just looking at this last one, they've described it in a different order to me, and therefore mine is a different version of it, but it's still right. So I'm happy with that. Now we'll just look at this backward transformation briefly. Just be aware that then there's questions for you to have a look at, so we're not going to get a chance to have a look at it. It says find the transformation that would have taken place. So we got y equals cos x, and they want to know what the equation will be to get there. So we've got a scale factor of 2 parallel to the x-axis, and that's why we've got the half x in here. There's a translation of 0 2, so there's a minus 2 at the end, or I like this, and a reflection in the x-axis. So we've also got this. So there you go. And none of that really seems a big surprise. So I want you to have a look at some of these, only some of these initially. There's another PowerPoint exercise 3A.2 coming up where you'll finish the rest of the questions. But for the moment, have a look at exercise 3A, questions 1, 2 and 3. Good luck.